Should've known better to see what I could see. My black shroud holding down my feelings.
Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
So let's go ahead and talk about some of the features of a mass spectrum. So we need to understand the relationship between mass spectra and resolution, presence of isotopes, fragmentation, etc. And so we're starting out with resolution. So in mass spectrometry, resolution is a measure of how well a mass spec separates ions of different mass. So low resolution mass spectrometry refers to instruments that are capable of distinguishing among ions of different nominal mass. So that's ions that differ by one or more atomic mass units, AMU. High-res mass spectrometry refers to instruments that are capable of distinguishing among ions that differ in precise masses by as little as 0.0001 AMU, which is extremely precise. To illustrate this, we can look at the compounds with the molecular formulas C3H6O and C3H8O. So these have nominal masses of 58 and 60 AMU and can be resolved by low resolution mass spectrometry. If instead we looked at the two molecules C3H8O versus C2H4O2, you could calculate that their nominal masses are both 60. And so low res is not going to be sufficient enough to differentiate between these two compounds. In fact, the difference in their precise masses is 0.03642 AMU. So you could use high resolution mass spec to differentiate between these two species. Another feature that's of particular interest to us, especially that's very useful when solving the molecular structure of a compound based on the mass spectrum, is looking at the presence of isotopes. So if we look at the mass spectrum of dopamine again, we find that the molecular ion peak appears at an M/Z of 153. If you look more closely at this mass spectrum, you see that there's a small peak at M/Z of 154. And that's from an ion that's 1 AMU heavier than the molecular ion of dopamine. This peak is actually the sum of 4 separate peaks, each of an AMU 154, and each corresponding to the presence in the ion of a single heavier isotope from hydrogen, carbon, oxygen, or nitrogen atom. Now, because this peak occurs or corresponds to an ion that's 1 AMU heavier than the molecular ion, it's called the M+1 peak. Now we're concerned, and we'll talk about here in this video, primarily the M+1 and M+2 peaks. Now virtually all of the elements common to organic compounds, including hydrogen, carbon, nitrogen, oxygen, sulfur, chlorine, bromine, are mixtures of isotopes. Exceptions are fluorine, phosphorus, and iodine, which occur in nature exclusively as F19, P31, and I-127. Now this table shows the average atomic weights for the elements most common to organic compounds, along with the masses and relative abundances in nature of the stable isotopes of each atom. In this table, the relative abundances are tabulated according to the number of atoms of the heavier isotope per 100 atoms of the most abundant isotope. So naturally occurring carbon, for example, is 98.9% C12 and 1.10% C13. So there's about 1.1 atoms of C13 for every 100 atoms of C12. So this can make a significant enough difference in the molecular total molecular mass to be able to see those peaks as M+1, small, but there in the mass spectrum. So for example, if you were to calculate the precise molecular mass of each one of these radical cations, you would see that the difference here just being a C12 on the left-hand side and a C13 on the right-hand side a difference of 1 AMU. Now looking at the relative abundances of the molecular ion peak, N+2 and N+1 peaks, we see that the most common elements that give rise to significant N+2 peaks are chlorine, bromine, and oxygen. The chlorine in nature is 75% Cl35 and about 25% Cl37. Thus, a ratio of M to N+2 peaks of approximately 3 to 1 is going to indicate the presence of a single chlorine atom in the compound. Similarly, bromine in nature is about 50.5% Br79 and about 50% Br81. So a ratio of the M to N+2 peaks of approximately 1 to 1 will indicate the presence of a single bromine atom in the compound. Now the contribution of oxygen 18 is only about 0.2% in nature, but it does make a major contribution to the N+2 peak in compounds that contain only carbon, hydrogen, nitrogen, and oxygen. Now, sulfur is the only other element here that's common to organic compounds that can give a significant N+2 peak as well. Now, let's use pentane, C5H12, to illustrate the relationship between the M and M+1 peaks. So pentane has a nominal mass of 72, and its molecular ion appears at an M/Z of 72. Now, in any sample of pentane, there's a probability that there will be a molecule in which one of the atoms of carbon is C13, the heavier isotope of carbon. This molecule is going to have a nominal mass of 73, and the molecular ion will appear at the M/Z of 73. Similarly, there's a probability that there will be a molecule in which one of the atoms of hydrogen is the heavier isotope, deuterium, or H2. The probability of each of these isotope substitutions occurring is related to the natural abundance of each isotope in the following way. So the percent relative abundance of the N+1 peak is the sum, sigma, of the percent abundance of the heavier isotope times the number of atoms in the formula. So we can do that for our pentane example. We have the sum of the relative abundance, or the natural occurrence, 1.11% of C13 times the number of carbon atoms, plus the same for the heavier isotope of hydrogen, 0.016 times the 12 hydrogens in the sample, in the compound. And so that comes out to 5.74%. Now this value is the relative percent abundance of the M+1 peak with respect to the M peak. So you can see here that the M+1 peak for pentane is almost entirely from carbon-13. And the same is true for other compounds containing only carbon and hydrogen. Now, because the M+1 peaks are relatively low in intensity compared to the molecular ion peak and often difficult to measure with any precision, they're not often useful for accurate determination of molecular formulas. But the N+1 and N+2 peaks can be useful for getting a rough idea of the number of carbons, oxygen, sulfurs, and halogen atoms in your compound. And so another trick that you can use whenever you're solving the mass spectra for a molecular formula of a compound is to take the percent abundance of the N+1 peak and then divide that by the relative abundance in nature for carbon-13. So that's 1.1%. And that's approximately equal to the number of carbons in your sample. Now let's consider the fragmentation of the molecular ions. To attain high efficiency of ion formation and to give reproducible mass spectra, it's common to use very, very high energy electrons. This energy is sufficient not only to dislodge one or more electrons from a molecule, but also cause extensive fragmentation. Now, this is because it's well in excess of bond dissociation enthalpies in organic molecules. So the fragments may be unstable as well and in turn break apart into even smaller fragments. However, only the positively charged cations here are going to be recorded or detected by mass spectrometry. So the molecular ions for some compounds have a sufficiently long lifetime in the analyzing chamber such that they are observed in the spectrum, particularly as the base or the most intense peak. So this is what I was mentioning before, that the most stable fragments make up the base peak of your spectrum. So the fragmentation pattern that you see and the relative abundances of the ions are unique for each compound under a given set of ionization conditions, and they're characteristic of that compound. And so the fragmentation patterns gives you valuable information about